Okay, the perceptron, it was first introduced by Frank Rosenblatt in the late 1950s, probably 1958 or something like that. And this is basically an extension of a McCulloch-Pitch model in 1943, and it uses the statistical separability theory, and somehow it's macroscopic calculus in probability. Okay, and he modeled photoperceptron in human eyes via retina, and the light comes in this retina. We have a sensory area S in the figure, and it actually generates source set -1, 0, +1. And we have associated unit A, and then we have a response area R. Okay, so this perceptron is basically a paradigm in reinforcement learning, in which we have activation of unit A if a critical point is exceeded, and the output becomes 1. If not, then the output becomes 0. Okay, so therefore he developed a perceptron convergence theorem. So mathematically, the perceptron will converge to some state. Okay. Sometimes it is vibrating, but vibrating is, in a wider sense, is some kind of convergence because it's bounded within some range. Okay, so in the learning process of two different kinds of patterns, we have two classes, either 0 or 1, or sometimes it's negative set or positive set. So either true or false. Okay, it is possible to classify two patterns within a finite cycle. This is very important. Within a finite cycle, you can find a solution. Okay, so the primitive perceptron learning algorithm, we have this algorithm here. Start label. We have a weight vector. Capital W0 is generated randomly. So sometimes we use Gaussian noise. Sometimes we use uniform kind of noise as the initial condition for these weight parameters. Okay, test. We have a vector x, boldface x, in positive set P or negative set N. Vector x is selected randomly, and if x, basically this vector is our training vector or learning. In the learning process, we have this input vector x, which is usually our training vector. If x in P, so that means x is, the output should be 1. Okay, so the output y or O should be 1. Okay, so x is in P, we already know. That's why we call this supervised learning. Okay, because we know the output, we know the labels. So x is in P, and the result, the initial capital W, 0t. Here t is the subscript that's saying the stepwise increment. Okay, so wt transpose x. So the inner product between our weight parameter capital Wt and the input vector capital X is greater than or equal to 0, then it satisfies the condition because after we applying threshold logic, it will become 1. So the output becomes 1 as output. So we go to it, we don't have to change the W, so that we go to test. So you pick up another vector, training vector X, in P or N. So if you take a look at the second one, if X is in P, so the output should be 1, the label is 1, and for this input vector X, for this training vector x, the inner product W transpose W3 transpose x is negative, then it does not satisfy the output condition. So we go to add. So from the third line below, okay, we have add. So set wt plus 1 equals to wt plus x and increase t, okay, by 1, and we go to test. We check another training vector. So what is add? W next weight parameter is the old parameter plus input vector. So this plus sign is one of the simplest operation, which will be effectively it will rotate the W vector, okay, towards X, okay. Okay, take a look at the test again. So we pick up another training vector X in PON. Now, if X is in N, so the output should be 0 or minus 1, if it is bipolar. And we check the inner product, WT transpose X is negative, then it satisfies the output condition. It is 0 or minus 1 after processing the threshold logic unit or nonlinear activation function. Okay, then it satisfies. So go to test. You pick up another training vector. You don't change anything. Now the fourth one, if X is in negative set, so that means the output should be either 0 or minus 1. And the inner product, WT transpose X is greater than or equal to 0. So it does not satisfy the output condition. So we go to subtract. Okay. Okay, take a look at subtract. Set WT plus 1 is WT minus X. So minus sign, minus operation is the simplest one. Actually, it rotates W vector and it goes farther away from the X vector. Okay, center vector of X. So there's an increase T and go to text and pick up another training vector. Okay. So basically add operation and subtract operation they are the simplest ones, but it actually rotates these weight parameter vectors. Okay, and then after finishing the whole scanning the whole training vector, okay, that's one learning cycle, and then we repeat until all X in P in the positive set or N in the negative set they are classified. After they are all classified, we stop. Okay, and this is done within a finite cycle. That's perceptron learning algorithm. Okay, we have problems in perceptron if it is single layered. Okay, from the paper of Marvin Minsky and Samuel Pepper in 1969, the name of the monograph is Perceptron. The theorem is they said perceptron will classify the learning patterns if they are linearly separable. So our net k, which is summation, I start from 1 to small n, wi multiplied by xi. This is just in definition of inner product between two vectors, w and x. And the output ok is, we have activation function small f net k. Okay. So inputs are set of predicates x1, x2, x3, etc. up to xn. We have n training element, okay, and this is just one training vector, capital X. If xi is 0, okay, xi is 0 if retina off, and xi is 1 if retina on, okay, and the weight parameters w is from we have element w1 up to wn, so we have n weight parameters, and the output should be 1 if net is greater than the threshold theta, and output y is 0 if net value is less than our bias theta, the threshold. So y is basically the same as OK over there, and y is the output of a TLU function, threshold logic unit function. So TLU is threshold logic unit, which divides the input space into two kinds of spaces, the positive set and the negative set. If it is in the positive set, the output should be 1. If it is in the negative set, the output is 0. Continuing the problems in perceptron with a single layered, perceptron, we need to classify patterns in this input space. Let's say we have 2 weights and 1 bias with a threshold logic unit. The bias should be greater than 1.5. The bias is 1.5, and the output should be greater than this theta if the output is 1, and less than 1.5 if the output is 0. So if you compute simple computation, will give you, because we have 2 input and 2 weight parameters with a bias, then we have this input space in 2-dimensional, and we can think of this lattice 0,0 at the origin, 1, 0, 0, 1, 1, 1 is rectangular type of lattice in this x1, x2 2-dimensional plane of input space. So we have a 2-dimensional input space and 2-dimensional weight space. Of course, we have a bias also. Now, what does that mean? Linear separability of classes. Because we have a linear equation, W1, x1 plus W2, x2, which is theta. You need to compare if it is greater than theta or less than theta. So let's say we have a W1 and W2 is just 1, and the net value is x1 plus x2, which is just, you need to compare with the 1.5. Okay? So the boundary condition of this line in 2-dimensional space is like this. Okay? If you rewrite this equation with respect to x2, then x2 is minus x1 plus 1.5. So we have a minus 45-degree angle slope of this linear line with 1.5 intersection in the x2 axis. Okay, if it is greater than this value, so that's the region of P up there, and below that line is the output should be negative. Okay, if you compute, then the output is less than 1.5, so you have the negative region. Okay. Okay. Therefore, with a single layered perceptron, we have this exclusive OR problems. Okay. The exclusive OR function is in the table over there. Input of the function is some kind of gate function. We have 2 input, x1, x2, 1 output, y. And if x1, x2 in the input space, we have 0, 0, 0, 1, 1, 0, 1, 1. It's a complete set. The output should be 0, 1, 1, 0. So if x1 is the same as x2, then the output is 0. If they are different, then the output is 1. So after applying to this activation function small f, then if net value is greater than or equal to theta, then the output is 1. If net value is less than theta, it will be 0. So the net function, net value is w1 x1 plus w2 x2. It's just the inner product between boldface w and boldface x vectors. Okay. So therefore, the output value output is 1 if net value w1x1 w plus w2x2 is greater than or equal to theta, and it is 0 if w1x1 plus w2x2 is less than the theta. Okay, so note that it is impossible for weight to be found because which is satisfy exclusive or input-output function specification by using just a single layered perceptron. Okay, why? Because this is a non-monotonic function. Okay, we have two valleys and two peaks. Okay. With this single layered perceptron, I said we have exclusive problems in general. And because it's non-monotonic function, it is impossible to find a solution with a single layered perceptron. Okay. So we need to define the definition, hyperplane or hyperline or hypercurve. They are the same terms actually that divide into two spaces, two subspaces, capital P or capital N. Okay. So we have an n-dimensional space which can be divided into two subspaces by using an n-1 dimensional object. So what does that mean? Okay, I have corrected some typo errors. Okay, if you have n inputs and n weight parameters with bias theta, then you need to combine this net value with bias. Okay, so basically that means the bias is another. It takes another parameter. So I will define this theta as minus w1, which is constant in this case. But sometimes if you want to generalize, then this is unknown also. So you need to use our learning procedure in order to find this bias. So bias is included, okay, later. So in this equation, at least one wi is not 0. So in n-1, with n-1 parameters, so I start from 1 to n-1 with sum this wi multiplied by xi. So this is n-1 dimensional hyperplane. Okay, so which is compared with the theta, which is our bias. Later it will be minus wn. Okay, if you choose this as a constant, then you lose 1 degree of freedom. Okay, so if you include this bias in the process of the learning algorithm, then you have n-dimensional space, and this can be divided into two subspaces. For example, in 3-dimensional space, we can divide those spaces into 3D subspaces by using 2-dimensional plane. So, in 2-dimensional space, we have a 1-dimensional line which is divided P set or N set, okay, positive set or negative set. Okay, definition, hidden node, node of the middle layer which solve this exclusive problems, okay, that is called multi-layer perceptron, okay, and in the middle layer we have hidden nodes distributed. Okay, let me give you just one example with the multi-layered perceptron. You can solve exclusive problems. I will choose arbitrary values for thresholds and weight parameters in this multi-layered perceptron. We have a hidden layer and two hidden nodes. Each one has an activation function, and output we have one node at the output. So here we have a for example, we have a multi-layer perceptron with 2 hidden units and 1 output unit, which solves exclusive problem. So threshold values, theta 1 is 0.4, theta 2 is 1.2, and theta 3 is chosen to be 0.5. And those weight parameters, W11, W21, W12, W22, they are all 1. And W31 is 0.6, and W32 is chosen to be minus 0.2. You just use these values somehow. Then you have multi-line perceptron in the figure. Okay? And the IO equation looks like this at the bottom equation. But you are not going to use this IO equation whatsoever. Okay? Too complex. And this is not the goal of neural nets. Okay? So these are all black box. Okay?
As a matter of fact, multi-layer perceptron is a combination of two linear separators. The first one is x1 plus x2 equals to 0.4. So therefore, if net1 is greater than 0.4, y1 becomes 1. Else, if net1 is less than 0.4, it's going to be y1 equals to 0. Second one is x1 plus x2 is 1.2, which saying if net2 is greater than 1.2, y2 becomes 1. As if net2 is less than 1.2, y2 equals to 0. And at the last layer, net value is 0.6, y1 minus 0.2, y2. We have three regions with two separators. If y1 equals to 1 and y2 equals to 1, net becomes 0.4, or y1 equals 0 and y2 becomes 0, and net is 0, then y becomes 0. Else, if y1 equals 1 and y2 equals 0, and we know net becomes 0.6, in this case we have y equals to 1. So we will take a look at the left hand input-output relations of this gate function, x1 and x2 as two inputs, and we get y as an output. So x1, x2, 0, 0, y becomes 0. x1, x2, 0, 1, then y becomes 1. x1, x2, 1, 2, 1, 0, then y becomes 1. If both x1, x2 are 1, then y becomes 0. So this will be a exclusive OR gate. And on the right hand side, we have three regions which generate either y equals 1 or y equals 0. So the blue region represent the region of which in which the output becomes 1, and in the region 2, the output becomes 0, the yellow region.
Okay, now, why is weight vectors, why is the weight vector perpendicular to the hyperplane? Okay, they are all perpendicular to hyperplane, our weight parameter vectors. Okay, the weight vector in two-dimensional space, for simplicity, W is W1, W2, and let's say this is red arrow, the direction, maybe size, represented in red arrow. And the hyperplane is net W1 x1 plus W2 x2, and this is compared with this net value, which is the bias sometimes. And x2 is minus W1 over W2 x1 plus net over W2. So the direction vector is the slope of this line, okay, for this hyperplane. So this is minus W2, W1. You can either put minus sign on top or the bottom, but anyway, the direction vector is represented by this the blue arrow, okay? And therefore, the inner product between those W which is W1, W2, and the direction vector minus W1, W2, you find in the product, they are always 0. Okay? So W1, W2 vector is perpendicular to minus W2, W1, either, or W1, W2 minus W1. Okay? So if you take a look at the figure, the W vector is in, this is represented by red arrow over there, okay? And blue arrow represents the slope of this hyperline in this case. And bring these two arrows into the origin, you will see how they are perpendicular, okay, 90 degrees between those weight vector and hyperplane or hypercurve.